Hi, I'm Malte Wessels from TU Braunschweig, and I'm going to talk about our work, Server-Side Request Forgery versus Developers, the study of Server-Side Request Forgeries, Defenses, and PHP applications. This is a joint work with Simon Koch and Giancarlo Pellegrino and Martin Jones, and Giancarlo is from CISPA. So consider this. You're sending a link to a friend in your instant messenger of your application, for example, to a nice kitten pic, and in most messengers you could get like a link preview, right? So this is the matrix application or the element client. And here the link preview is generated on the server side. This is like the typical example for a server-side request. There are lots of other examples, for example, APIs on the server side in general, or webhooks in your Git or GitLab instance. And the implementation looks like something like this. You have a chat client who requests a preview for a given link, in this case, the Unsplash link to the kitten. And the chat server then has to fetch that request from a remote that hosts the pic. It returns the picture and forwards it to the client. So on the right-hand side, the communication between the chat client and the web client server, is the server-side request, because the server is doing a request for us. But this can go wrong. And the attack is called Server-Side Request Forgery, because a client can forge us to request unexpected targets. The typical example is requesting localhost. So the user, on this case an attacker, could specify localhost as a domain, forcing the chat application server to request itself. This might trigger like some internal APIs behind the firewall or the internal network, and could lead to multiple things. Previous work has shown that there are many attacks and many ways that this can go wrong. And I want to show you another one, because an attacker could, for example, misuse this chat server to deliver a payload to remote location. For example, they could send this attack payload to their target, use the chat service as a proxy. The attack payload exploits the remote target and hides its steps behind the chat server. So this is basically obfuscation of the origin of the attack, right? So for this work, we conducted a literature survey of all existing academic and non-academic works to compile a list of all known attacks and defenses. This is too much for now, but I'm just going to talk about like the perfect defense. So if you're a developer and you're implementing a server-side request feature, you have to think about a lot of things. You have to think about compiling like a sound either deny or allow list. So a list of targets that are allowed to request or that you only want to request or not, right? And you have to think about how you validate against this list, either maybe via the URL or via the DNS request. And you have to think about the configuration of your requesting client. So do you want to allow redirections? And if you are allowing redirections, you have to do all of these checks we're now discussing for every step of the redirection. You have to also think about rate limits, both for the in and the output, to mitigate DDoS attacks or DOS attacks. And you have to think about what you're doing with the response. Because if you're just taking the response and sending to the client back, you can be misused as a proxy. And let's look deeper into this validation thing. Let's say we have a deny list, so a list of targets we don't want to request. We could just go ahead and say, yeah, okay, we take the URL from the user, we parse it, we get the host, we check it against a list of known hosts that are bad, and if it's in the list, we stop with the request. Otherwise, we conduct our server-side request. But what does conducting this request actually mean? For this, the system has to resolve the domain to the IP, because the request is obviously made against the IP address and not the domain itself, right? But there's a certain mismatch here, because we're checking against the host, but we are requesting against the IP address. An attacker can use this, for example, by using a domain like fbi.com, which resolves to localhost. And so he's evading your list. And of course, you can't collect all of these domains that resolve to localhost. And even if you could, an attacker could just go ahead and register a new domain, which also resolves to localhost. So obviously, using a host-based list is not suitable for this case. So a possible fix is using a DNS request. You pass the host again, resolve it, get an IP address, check the IP against a list of known bad IPs, and if it's in this list, you stop. And if you continue, again, what does continuing really mean? The system has to take the URL, resolve it again, and then trigger the actual request against the IP address. But here we are doing the DNS resolution twice. And because there's a certain timing here, we have a time of check to time of use bug, right? Because this is called DNS rebinding in this context, where we have a malicious or like a DNS server that rapidly changes between two IP addresses. So if an attacker is lucky, the domain will resolve to some benign IP in the first check, but to like a malicious IP or like localhost in the second step. So the actual fix for this is to use something called DNS pinning or IP pinning, where we're using the actual IP we use for the check, again, for the actual server-side request. Okay, and this is kind of annoying to implement, so you most certainly want to use like a library that does that for you. So why am I telling you all this? My point is that defending against server-side request forgery is kind of hard. So we wondered, are developers doing this actually correctly? And there are like two questions for this. Are they using like off-the-shelf defenses, or are they maybe building their own? And to solve these questions, we're looking at PHP. PHP still powers, as we've seen previously, most of the web, and we've pulled 30,000 repositories from GitHub that use PHP as a language. We then also took a look at the surrounding ecosystem of PHP. We've compiled a list of every framework in PHP that supports server-side requests natively, and out of these, only one, namely Symfony, supports a defense. WordPress does provide some sanitization functions, but they're broken. You can check the paper for the details. We've also looked at the available HTTP clients for PHP, where they're like the most common are the two built-ins, the PHP standard library, like file get contents, and the PHP curl extension, and a lot of other third-party clients. Out of these, only specific third-party clients designed to be safe against SSRF, namely SafeCurl and two of its forks, are safer. And they're available as SafeCurl and the fork SafeURL, and as a plugin available for the HTTP plug ecosystem. So, however, we conducted a prevalence study in our dataset of 30,000 repositories, and we found that only 4 applications are using these safer clients. Out of these 4, one is actually by one of the same maintainers that is maintaining the safer client. So in reality, only like 3 third-party applications are using safer clients. So if people are not using like ready off-the-shelf safe clients, are they maybe doing it by themselves? So to answer this question, we are conducting a static data flow analysis on PHP. We do this to extract candidates that might be vulnerable to SSRF and check these manually. And to do this, we take the PHP source code and dump it into the PHP engine. And as you might know or might not know, PHP has a virtual machine inside which runs on opcodes, and we get this opcode, this bytecode from the PHP engine itself. This has the benefit for us that this comes also with the control flow graph. So we take these bytecodes as our AST and the control flow graph from the PHP engine, and we construct a PHP bytecode CPG. We use like an off-the-shelf data flow algorithm to get to the data flow. We construct a call graph, and then we implement a tool that can look for SSRF candidates and data flow in this CPG. We handcrafted a list of things by scanning the PHP documentations, and we implemented this tool to also reconstruct the string, so we can somewhat see what string is landing up in these things. So, as our results and our insights, we, as a first step, filtered only for those findings that are in actual applications, and not, for example, some CTF challenges and vulnerable applications that are vulnerable by design, which are a lot of on GitHub. And we filtered for those data flows where the user input or the attacker input is at the start, because only then the attacker has like full control over the URL. And we found 104 flows and applications where the domain is the attacker controlled, so they're vulnerable. And we found 2 applications with the proper defense. Both of them are doing a low listing. And we haven't found an application that is using DNS resolution, which is required to do a safe denial-based approach. So our main takeaway is that although we as a research community are well aware of the risks and the attacks and solutions in regards to server-side request and server-side request forgery, most of the people are still doing it wrong. So thank you very much for your attention. You can find our artifacts, which are functional, at the QR code, including our PHP bytecode code property graph. Thank you.